So the first disease that we're going to look at is herpes. Now, herpes is a non-life-threatening sexually transmitted disease, and a lot of what was discovered in treatments for herpes became important later on. Herpes is a lifelong condition. Once you contract it as a virus, you have it for life, and it flares up from time to time, like many viral infections do, and in times of flare-up, people would take some sort of treatment for it. And the treatment that was developed in the 1970s is called Acyclovir. And we're going to think about how Acyclovir works because it's quite a rationally designed drug. So it was developed in the 1970s. Worth noting, this is a long time after people started working on antibiotics. That work really started in the 1920s and 30s, as we saw last week. Viruses are a much more challenging target because they don't have their own metabolism. They use your metabolism to reproduce, and that's what makes them so challenging to treat, because you run the risk of interfering in your own important metabolic processes. So, Acyclovir, we can say it is a rational design. And what it does is it mimics a DNA base. Obviously, this was building on information from the 1940s and 50s, where the structure of DNA had become discovered. The function of DNA was being discovered in the 40s and 50s. That led to breakthroughs in medicinal chemistry in the 60s and 70s, thinking about DNA as a valid target. And so that's why that timeline works out for this particular drug. It builds on Crick, Watson, Franklin and Wilkins's work. So what it aims to do is it aims to stop viral replication. Because really, that's the one thing that you need to do with a virus. You need to stop it making copies of itself within the cells of your body. And it does this in a very specific way. So we'll come and look at the structures and then we'll go back and make a few notes above. So you can see Acyclovir is very similar to guanosine. This is the RNA version with both OHs on the bottom. And if you were building this into a nucleic acid, if you were building DNA, you build a phosphate linkage through this OH group here. And you build a phosphate linkage through this OH group here. And I've deliberately drawn Acyclovir in a suggestive way. You can see the bottom of that ribose ring, the bottom of the sugar ring, is missing in the Acyclovir. There's nothing in the bottom part of the molecule to carry on the DNA chain. So what we have here is a missing OH. So that means that if the virus is trying to make DNA within your cells, and there's lots of Acyclovir around, the virus will grab an Acyclovir instead of a guanosine, build it into the DNA, it's got all the right hydrogen bonding bits, and then the chain will terminate because there's no way of building the phosphate chain out of the bottom of the Acyclovir. So really what you're aiming to do is replace the guanosine within your herpes-infected cells with Acyclovir so that you terminate the chains, and that will prevent the reproduction or the effective reproduction of the virus. So it aims to stop viral replication. We can say a bit more now. There is a missing OH group on Acyclovir. The virus builds Acyclovir into DNA, but the chain cannot extend. Acyclovir is effectively, again thinking in polymer chemistry language, which is useful because DNA is a polymer, acyclovir acts as a chain terminator. It terminates the growth of the DNA polymer, and it terminates it before you've built the full DNA chain. And what that will do is that will stop replication. Because if you can't replicate all the genetic material of the virus can't make its proteins properly, it can't make a copy of its coat and fill it up with more DNA and go on to reproduce itself. You're stopping that process of viral replication. And you may wonder why this doesn't affect all your cells. Why is acyclovir not toxic to all your cells? Because of course all your cells are reproducing DNA, but the key thing is that an enzyme in the virus phosphorylates the OH 3,000 times faster than in normal human cells. So actually, the virus is replicating its DNA 3,000 times faster than a normal human cell would. And so that's why this is effectively a virus-activated prodrug. It's much more problematic in cells that are infected with the herpes virus because of that rapid activation, and the acyclovir gets built into the DNA. So there's a note at the bottom here, because this tells a bit of the history of how this drug was developed. So acyclovir does prevent rapid replication of DNA. And the other thing in your body, apart from viruses, that very rapidly would replicate DNA is a tumour cell. Cancer cells very rapidly replicate their DNA. So this mode of action is relevant in treating tumours, which you'll explore in more detail later in this module with Martin Facioni, who'll talk about cancer chemotherapy. Okay? And this early work on acyclovir built on the pioneering work in anti-cancer chemotherapy. So once the structure of DNA was discovered in the 40s, they realized that DNA was replicating fast. They realized that DNA was a target. The main thing they were doing was trying to develop anti-cancer drugs in the 1960s. And acyclovir was originally designed as an anti-cancer agent, but wasn't very suitable for use for different reasons. And so they then tested it against the herpes virus and found that it was active against that, and it went on. And it is still the frontline treatment. If you have herpes, you'll still be given acyclovir. In fact, it is quite a broad spectrum antiviral treatment. So if you're, say, an immune suppressed patient or somebody who they don't want to pick up a virus and you're exposed to a virus, they'll give you acyclovir as a way of trying to knock the virus down a little bit. So it's reasonably broad spectrum, but it certainly doesn't kill the virus, it doesn't destroy it, it doesn't get rid of it from your body, it simply slows down its replication rate. Okay? And that's quite true of most antiviral treatments that we're going to look at. Because it's not a living organism, so how can you kill a virus, right? It's a very challenging issue.